Let's take a look at the night sky inside the spring skies. What I had to do is I picked a particular time of the evening for a particular month, and we'll discuss exactly how I decided to do that. But let's go ahead and start with this. What I have is this is a map of the entire celestial sphere. It's essentially, if you've seen, I've got a celestial sphere right up there, that clear sphere, and there's also the blue one as well. And what we've taken with those celestial spheres is that we have smashed those down into a map, and it does something kind of odd when you make a map like this. It elongates the things that are at the poles. However, at the middle, everything's just about right. So the constellations, the stars, the shapes that you might see are accurate there, but then they get a little bit warped. As a matter of fact, there is the cup of the Little Dipper, and there's the end of the handle over there. It's stretched all the way from one side off to the other. So things are strangely warped when you look at a Mercator map like this. That pink line that's going right through the middle is the celestial equator. The celestial equator is bifurcating the northern and southern hemispheres of the celestial sphere. And a really easy way to think about the celestial equator is to think about the equator around the Earth. If you were to extend the equator around the Earth out into space against this kind of make-believe celestial sphere around us, that would be the celestial equator. So the celestial equator is right on top of the Earth's equator itself. That yellow line that you see that goes through here, right here, that is called the ecliptic. And the ecliptic is the plane of the solar system. This is where you will find any of the planets. This is where you'll find the moon. This is where you'll find the sun, somewhere on this ecliptic. Now, the reason why it has this interesting sinusoidal shape is because it too is a circle around the Earth, but it's tilted. For example, here we have the equator. Here we have the ecliptic. The ecliptic is tilted because the Earth is tilted 23.5 degrees. And if I were to flatten this map, I can only have one of these rings come out straight. So the celestial equator does this, right? But if I have another one that's tilted and I flatten that map, look at what it does. It does this. And it gives us that sinusoidal curve that we see. So here we would have the sun traveling along the different constellations throughout the year, the planets traveling along the different constellations throughout the year. I know it's hard to see the actual names of the constellations because this map is so small, but you might be able to see these odd, jagged, yellow puzzle pieces. There are 88 of these puzzle pieces. These are around 88 different constellations, and that's it. There are thousands of other patterns. We call them asterisms, but there are only 88 constellations. A group of astronomers in the early 1900s, they said, whoa, we've just got so many constellations, we need to put our foot down. And they chose 88. 48 of those are ancient. They come from Greek and Roman and maybe even Sumerian myths. And then they added some modern constellations, another 40 constellations that are made up of animals, scientific instruments. There's a constellation named Telescopium, Microscopium. So they're really proud of their scientific instruments. And those are mostly in the southern hemisphere. If we were to take all 88 of these puzzle pieces and put them together, they would create this sphere around us. Every star in the sky is in just one constellation. One constellation and one constellation only. Different objects, galaxies, nebula, star clusters, they can span different constellations, but every star is in a single constellation. This huge sinusoidal curve right there, by the way, that is the Milky Way. The entire solar system is on its side going through, orbiting through the Milky Way galaxy. So it has an even larger curve on this view. Here we can see the Earth. Actually, let me go back one here. I just realized right over here, that's where the sun is right now. When we look at that yellow curve there, we can see different dates. And you may not see the dates themselves because they're so small here, but you can visually see it because this here, where this hump right above the celestial equator, that's when the sun is at its highest point above the celestial equator. That's when the sun is up longest. We have the longest day of the year. That's the summer solstice right there. If that's the summer solstice, you can probably take a guess what that is, can't you? There's the winter solstice. And then where the ecliptic and the celestial equator meet, here and on either side of the map, here and here, where they cross each other, it's equal. That's the equinox. When the sun is here or here, we have our equinox. So this is March, April, May, June, about June 21st. It's always around the 21st. June, July, August, September, October, actually about September 21st for the equinox. September, October, November, December 21st. It can be the 22nd, 23rd, but it's around the 21st. December, October, November, December, January, February, March again. This is the same as this here. This is where the sun is right now, and all these constellations would be up during the daytime. So these are the constellations that we'd be seeing in the evening sky right now. As the Earth orbits around the sun, we are privy to different parts of the Milky Way galaxy. So there are some constellations that are up year-round and all night. We'll talk about those. Those are our circumpolar constellations. But in the south, we get to see a number of different constellations as the Earth orbits around the sun. During the summertime, we are looking towards the center of the galaxy. During the wintertime, we're looking out the spiral arms of our galaxy. This is why during the wintertime, stars seem to be brighter for a number of reasons. One, yes, temperature has something to do with it. Also, during the wintertime, you have less moisture in the air, but you also have a backdrop of darkness. Whereas in the summertime, you're looking towards the center of our galaxy, and you have a backdrop of billions and billions of stars. So the stars that you do see, there's not as much contrast, and they do not seem quite as bright. Right now, we are right in between winter and summer. We're looking out the arms of our galaxy. Here, spring is known as galaxy season. We see a number of other galaxies in the sky during this particular time. If we wait until summertime, the Milky Way will rise and get higher and higher and higher. And I imagine everyone here has had a chance to see the Milky Way. That's the nice thing about living here in Nebraska, here in Lincoln. We do not have to travel very many miles to get out of town, to get away from the light pollution, and we can enjoy beautiful, beautiful night skies and easily see the Milky Way. But realize there are so many people in this country that live in cities and light polluted areas that are so bad they never get a chance. And when I was at the University of Nebraska-Lincoln, I would have my students, I'd ask them, how many of you have seen the Milky Way? Maybe 2 or 3 in a room full of 100 would raise their hand, which always blew me away. And that's why I want them to get out here to Branch Oak Observatory so they would get a chance to see the Milky Way. It might not be this bright, but you can see it. And if you ever get a chance to head out to the Nebraska Star Party, which is south of Valentine, those skies are spectacular. The sky is so dark, and the stars are so bright, you can hold out your hand, and the starlight from the Milky Way will cast a shadow of your hand onto the ground. That is how dark it is. That's how bright the stars are. Absolutely phenomenal. Here we have a representation of the spring sky. And since I do the spring program, followed by the summer program, followed by the fall program, I had to pick 3 months of span, and we have slightly different times. So this is the sky that you would see at 1 a.m. on March 15th, 11 p.m. on April 15th. So we would need to go on outside and then wait a couple hours, and then this would be the sky that you would see. And it'd be 9 p.m. Next month. Let's go ahead and rotate this entire thing and zoom in on the north. Now, when we do so, there is one star that sticks out like a sore thumb right there in the middle. It's a star named Polaris, but of course Polaris goes by a much more popular name, doesn't it? Polaris is also known as the North Star. There it is. There's the North Star. The North Star is not, I repeat, it is not the brightest star in the sky. This is a very common misconception, and I think the reason why a lot of people think that is because it's famous, and they figure it must be famous for some reason. It's actually the 49th brightest in the sky. So while it's not bad, it's nowhere close to being the brightest. Polaris, the North Star, is famous because of its position in the sky and what it's been used for hundreds and hundreds of years. The North Star is very, very close to the North Celestial Pole. You'll remember the Earth is tilted on its axis. And if we were to extend this axis, actually I would need to turn it this way. If we were to extend this axis into space, that axis would be pointing right at the North Celestial Pole, which you'll see is very close to the North Star. It's not exactly on it, but it's pretty darn close. And throughout the night, as the Earth rotates on its axis, stars make circles around the North Star, larger and larger and larger circles. Once you get far enough away from the North Star, that circle is so big, the stars rise and set. So the stars that do not rise and set, that are up all night long, all year long, those are called circumpolar stars, and the constellations that they're in are circumpolar constellations. The stars that rise and set are very cleverly called rise and set stars. And then the stars that you are unable to see, that are orbiting around or circling the South Celestial Pole, those are the never-rise stars. But which stars are circumpolar, which stars are rise and set, which stars are never rise, completely depends on where you are on the Earth. Because while the North Star is always in the north, it does get higher and lower depending on your latitude. In fact, our latitude, about 41 degrees north latitude. The altitude of the North Star above the horizon is equal to your latitude. So the North Star is 41 degrees above the horizon. So if you ever find yourself lost out in the middle of nowhere, maybe, God forbid, kidnapped on a boat, and you have no idea where you are, if you measure the altitude of the North Star above the horizon, it will tell you what your latitude is. Now, longitude, that's a whole other ball of wax that requires a watch and a clock. It's very much more difficult. But there is your actual latitude right there. And if you were to travel to North Dakota, North Star would be a little higher in the sky. Alaska, even higher in the sky. And if you were at the North Pole of the Earth, where would the North Star be? That's right. Be right above your head. And think about what that means. If the stars are making circles around the North Star, that means at the North Pole, every star is a circumpolar star. If you chose a star right on the horizon throughout the year, it would do this. And actually throughout a 24-hour day as well. It would never rise and set. If you're at the North Pole, you're stuck with the same constellations year-round. Conversely, if you're at the equator, as you travel towards the equator, the North Star gets lower and lower and lower and lower. Then finally, when you're on the equator, no more North Star. It's right on the horizon. The North Celestial Pole is there. The South Celestial Pole is there. You can't see those. And all the stars do this. They're all rise and set stars. Every single one of them. Stars come straight up and east and go down straight west behind you. The easiest way to find the North Star, as you probably have already noticed, the North Star is right in the end of the handle of Ursa Minor, or the Little Dipper. Problem is, the Little Dipper is a lot more difficult to see than people think it is. The Big Dipper, however, is very easy to find. It's nice and bright, easy to locate. So step one is to locate the Big Dipper. The Big Dipper is going to be in the north. It might be in the northwest. It might be in the north. It might be in the northeast. It depends on the time of night and the time of year that you're going out. But it will always be somewhere in the north. And if you use these two stars right here in the cup of the Big Dipper, these are known as the pointer stars. They will point you right to the North Star Polaris. Polaris is then in the end of the handle of the Little Dipper. You'll notice it does not say Little Dipper here and Big Dipper, does it? Because the Little Dipper and Big Dipper are not constellations, and that's always a surprise to people. They are asterisms. different countries, different cultures, different time periods. Everyone has formed their own dot-to-dot imaginary pictures in the sky. Even today, we don't even have to time travel here. Even today, if you went to a planetarium or an observatory in Europe, depending on where you are, they might call that the Big Dipper, they might call it the plow, they might call it the wagon. Whereas here in North America, we know it as the Big Dipper. We do have two constellations here. The Big Dipper is inside of Ursa Major, the Big Bear or the Greater Bear. Right now, the bear at 11 o'clock is upside down. The handle is the tail of the bear. His back leg extends out like so. His stomach, chest, front leg, there's his paw right there. The bottom of his neck, the tip of his nose, top of his head, all the way to the base of his tail. Now, as astronomers, we are not all about looking for constellations, but we do use these constellations as a map, a treasure map, to find beautiful hidden treasures, galaxies, nebula, star clusters. Because by star hopping, we're able to find the general location. For example, I know right above the head of Ursa Major, we have two galaxies. One is named M81, also known as Bode's Galaxy. The other is M82, also known as the Cigar Galaxy. These are about 11 million light years away from us. The distance between these is about 150,000 light years across, which is about the size of our own Milky Way galaxy. So our own galaxy, which is larger than these two, would fit right there nicely in between those two galaxies. We have a beautiful, what I really like about these two galaxies is that generally you can get them in the same field of view in a telescope, and one is just like this, face on, the other one is edge on. So you kind of get to see both edges of the spectrum, so to speak, on those two galaxies. What exactly is a light year? I know many of you already know this, but let's go over this anyway. A light year is the distance that light travels in 1 year. So even though it has the word year in it, it's not a measure of time, it's a measure of distance. A light year is it's about 6 trillion miles. If you take the number of seconds in a year, 3.15 times 10 to the 7th power seconds, multiply that by 186,000 miles per second for the speed of light. Also, if you're in a metric, 2.99 times 10 to the 8th power meters per second. Light's really fast. If I were to take my laser pointer and hit the laser pointer and at the same time drop my laser pointer onto the ground, it would take about a half of a second to hit the ground at this distance here. In a half a second, that light could travel around the Earth 3.5 times. Light is really fast, but we are talking about distances that are so great, it even takes light a good deal of time to get to these places. The nearest star to us after the sun is 8.3 light minutes away from us, but the nearest star to us after the sun is 4.25 light years away, Proxima Centauri. So when you look at Proxima Centauri, you are literally looking back in time. You're looking at what it looked like 4.25 years ago. Astronomers call this look-back time. The Great Orion Nebula, which is up right now, it's in the constellation of Orion the Hunter, one of the great constellations in the winter skies, is 1,344 light years away. And the Andromeda Galaxy, the next large spiral-type galaxy, it's even bigger than our own, to us, is 2.5 million light years away. And when you look at the Andromeda Galaxy, which, believe it or not, you can see it with the unaided eye. You have to have good eyes, you have to have clear skies, and you have to know exactly where to look, but you can see the Andromeda Galaxy with the unaided eye. You're looking at what it looked like 2.5 million years ago. Astronomers were time travelers, and our telescopes are like time machines. I turned this on to show it to you. I'll have to turn it back on again a little bit. Right down here at the tail of the bear, we have the Whirlpool Galaxy, M51. This one's a little further away. This is 31 million light years away. It's even further. This is an absolutely beautiful galaxy, beautiful spiral galaxy with an arm that is curling around a smaller galaxy, NGC 5195. It's just saying, come on over. And it's adding that galaxy into itself. This is one way that galaxies change their shape over time, is through gravitational interaction and sometimes even collisions with other galaxies. That Andromeda galaxy that we talked about, that galaxy, unlike most galaxies that are moving away from us, the Andromeda galaxy it's coming right at us. And yeah.
When you talk about collision, do they actually physically collide? Because
yes and no. So an analogy I like to use is think of 2 handfuls of sand and throwing them up. There's a lot of space in between those, and those are like the stars. So when these galaxies collide, there's so much more space in between them. So what happens is that they warp, their shapes warp. Our own sun, when the Andromeda galaxy and the Milky Way galaxy collide with one another in about 5 billion years, as they get closer and closer, they're just going to warp their shape. And then when they collide, they'll kind of undulate until they finally stop in an elliptical shape. So our own sun, if it's still around at that time, because its fuel will be running out around that at the same time, our own sun that was born inside of one kind of galaxy, a spiral galaxy, will then live its short final years in an elliptical style galaxy. So again, this is how galaxies change their shape, is through gravitational interaction and collisions with other galaxies. It doesn't destroy stars, it actually enhances new star birth, because there's a lot of interstellar medium between those stars, and it enhances the possibility of new stars being born. The second star in from the end of the handle of the Big Dipper, if you have good eyes, if it's clear tonight, take a look at the second star in from the end of the handle of the Big Dipper, and you may just be able to separate 2 stars there, Mizar and Alcor. There's kind of an old mythos that these were used as an eye test for young warriors to see if they have good eyes. I've got terrible eyes and I can see them, so I don't know much about that. But here's what's interesting about Mizar and Alcor. If we were to analyze these, Mizar here in itself is what is called a visual binary. A visual binary. Binary meaning that it's orbiting around a common center of mass. They really are gravitationally attracted to each other. Visual in the sense that we can break them apart with a telescope. So Mizar is broken up into Mizar A and Mizar B, and both Mizar A and Mizar B are what are called spectroscopic binaries, which just means that we cannot separate the stars with a visual telescope, but we are able to see them using a spectrometer, looking at their red shift and their blue shift as these stars are orbiting around each other. Alcor turns out to be a visual binary. So where we see one star, there isn't one, there isn't 2, there are 6 stars, all orbiting around this common center of mass, doing this very convoluted, complex dance around each other. Let's go ahead and rotate the skies and take a look in the west. Right down here, low in the west, the Gemini twins, actually it's in this direction, the Gemini twins will be just going down. When we go out, they'll be a little higher in the sky because we'll be going out a little bit earlier, depending on if the sky cooperates. Castor and Pollux are not only the names of the 2 stars, they're also the names of the twins, the Gemini twins. Castor and Pollux, and it's kind of 2 stick figures that are standing right next to each other, and we'll point those out in the actual night sky, the Gemini twins. Right now, the planet Mars is inside of the Gemini twins, and we'll get a chance to see Mars tonight. Jupiter is up as well, but by the time 11 o'clock rolls by, Jupiter is a little too low for me to have had in this program, but we'll get a chance to see it in the actual sky tonight if it's clear. There's the ecliptic, there's the path that the sun, the moon, and all the planets take as they travel through these constellations. Ancient astronomers, they noticed that the planets traveled through different constellations, and they figured, hey, those must be different. Those constellations must be special. And they named those the constellations of the zodiac. So even though we are astronomers here and not astrologers, the constellations of the zodiac are a real thing, and they are actually in the night sky. There used to be 13 constellations of the zodiac, but when we moved over to the Gregorian calendar with 12 months, we had to kick out Ophiuchus the snake handler was the constellation of the zodiac that we had. So if you were born as Ophiuchus, that would have been a long time ago. No more Ophiuchus the snake handler. If we move along our path, we'll be able to see, actually right down here at the foot of Gemini. I'm surprised I have this in here because it's so low in the sky right now, but we are able to see it earlier in the evening. We have two beautiful star clusters. These are both what are called open clusters as opposed to globular clusters. This one sure looks like a globular cluster, but it's not. Open clusters are generally made up of younger, hot blue stars that are maybe just a few million years old. This is a relatively old open cluster, and if you've ever heard of the cluster, the Pleiades, also known as the Seven Sisters, it's up tonight, we'll point it out. The Pleiades are an open cluster of stars, absolutely beautiful in the night sky. This cluster here is 2,800 light years away. This one is about 12,000 light years away. It's much, much further. That's why it looks a little fainter and smaller in size. Right in between Gemini and Leo here, we have the faintest of all the constellations of the zodiac. It's very, very difficult to see. Cancer the Crab. But even though Cancer the Crab is very faint constellation, hidden inside of it is an absolutely beautiful cluster of stars named the Beehive Cluster, and it is absolutely beautiful in a common pair of binoculars. It is only about 600 light years away, so relatively close, absolutely beautiful. It also goes by the name Praesepe, which means manger. I can actually see the Beehive Cluster before I can see the constellation. That's kind of backwards of how it usually works. Usually you find the constellation, that helps you find the object. Here, can just barely make out that object before I even see the constellation. In the sky, we have an asterism right here. This backwards question mark is called the sickle, and the sickle is in the front half of Leo, the lion. There's the head of Leo, there's his mane, his front leg, his body, his back leg, and his tail. Right below Leo the lion is one of my absolute favorite groupings of galaxies. This is a picture that I took with this little telescope. This little thing took that. It's absolutely, it blows me away. This little thing, what it does is it takes a 10-second image, and then it takes another 10-second image, then it takes another 10-second image, and it stacks those images on top of each other. So the longer you wait, the image gets better and better and better. And after 30 seconds, this thing outperforms every telescope here at the observatory. It kind of is infuriating, but it's also amazing. And these have really changed the way we do things in astronomy education. They are wonderful. But yeah, took that right here from Branched Oak Observatory with this little telescope. And after, it was actually long exposure. This is not 30 seconds. That's about 1 hour, about 60 minutes of exposure on that image.
So does the camera have to kind of, or the telescope?
Yes.
Have to kind of follow or blur? Right?
That's a can of worms, and so I'm going to make it as short as possible, but you are absolutely right. Usually with the telescope, none of these work. Well, this one kind of does. You have what's called an equatorial mount. Back in the old days, 10 years ago, I mean, this has really changed. You would always have to have your telescope, if you were doing astrophotography, it had to be polar line. That way, the motor would counteract the rotation of the Earth. The Earth goes one way, the motor goes the other way. You point it at an object and it follows it. What this does is it not only and yes, it is following, but because it's out azimuth, it has to go in steps. So, not too many years ago, an astronomer would say, yeah, you can't use an out azimuth telescope for astrophotography because what happens is you get something called field rotation. The object, not only does it move, but the object will rotate. So this software not only is stacking software, it also derotates it electronically as well. It's absolutely incredible that they were able to get both of those abilities within the same instrument. Let's go ahead and move the sky here. Take a look in the south. Right up here we see Virgo, and you'll notice Virgo, her legs are out, her arms are up in the air. It doesn't look like she has a head here, but right where her head would be, we have thousands, about 1,300 galaxies. This is called the Virgo cluster of galaxies. And a number of them are those Messier objects, those objects that Charles Messier put together, including M87. M87 is a very, very important one because not too many years ago, we were able to discover for the very first time, 2017, we were able to use a number of telescopes. It was a set of telescopes called the Event Horizon telescopes that all worked together to look into the heart of this galaxy and for the first time take a picture of a black hole. This is the event horizon of a supermassive black hole. This is not a stellar black hole. This is a supermassive black hole. This particular one has billions and billions of solar masses inside of it. And to give you an idea of the event horizon here, that's the path of no return. Light can go around, but once it steps on the other side of the event horizon, it's all over for that light. That event horizon is larger than our solar system. It's a very, very, very big event horizon. And this is all that energy that is falling into the black hole or curving around it. Let's wrap up here with just a few more constellations. Right up here we have Boötes the herdsman. You will remember maybe in the program that we're watching previously, they said follow the arc of the handle, follow the arc to Arcturus. Arcturus is the second brightest star in the northern celestial hemisphere, and it's the fourth brightest star in the entire celestial sphere. So it's a very, very bright star in the sky inside of a constellation named Boötes the herdsman. Looks a little bit more like a boot. This would be the top of the western boot. This would be the toe, and that would be the heel. Right next to it, we find M3, and this is the globular cluster that was mentioned in that program. Unlike an open cluster that has dozens, maybe hundreds of stars, globular clusters have hundreds of thousands of stars, upwards of 500,000 stars within these clusters. They are only about 2 or 3 light years from each other when you get deep within the globular cluster itself. Usually I do not mention Corona Borealis, but let me mention this very quickly because there's something exciting going on right now that maybe you've heard about. This is the crown, the northern crown. Each one of those stars is a jewel in the northern crown. That star right there, its name is Gemma. It goes by a few other names, but Gemma, that's where we get the word gem from, right there. Right off of Corona Borealis, about right there, we have a star. You won't see it here, and you will not see it with the unaided eye, so you'll just have to take my word for it. There's a star named TCRB, or T Coronae Borealis. And T Coronae Borealis is a binary star system between a white dwarf and a red giant. They are orbiting around each other. And the white dwarf, which is actually more massive than the red giant, the white dwarf is pulling material off of the red giant. It's called the donor star. And it's pulling this material, dumping it onto its surface. It heats up, gets hotter and hotter and hotter, and every 80 years, it flares up in what is called a nova. Not a supernova, but a nova. The last time it happened was 79 years ago. So there is a lot of thought that it's going to happen any time now, from now until throughout next year. But there are some things that are going on, some changes that we've seen. There was what's called a post-burst dip that happened last time, that happened late last year, or happened last year rather, and it's thought that this star is going to go nova anytime now. Anytime. It could happen tonight, probably, but it could happen anytime. And that is really exciting. And while aurora and solar eclipses and lunar eclipses are amazing things, this is a true once-in-a-lifetime event. Something very exciting for us astronomers. It will not be so bright that you'll see it in the daytime sky, and it won't be so bright that you'll be able to just go, oh, point it out in the night sky. But if you do know where to look and you know what to look for, you will be able to see it. And when that star that is right there goes off, it will be as bright as Gemma here. It will be noticeable. Very exciting. Right down here we have Hercules the hero. Very famous hero in Greek mythology. Unfortunately, the constellation isn't that bright. But right in the side of Hercules, we have perhaps the greatest of all the globular clusters, M13, the Hercules star cluster. It's only 22,000 light years away. Very, very dense. Somewhere between 500, maybe even 800,000 stars compressed within this particular globular cluster. And this globular cluster was discovered by Edmund Halley, the gentleman who discovered Halley's Comet. Beautiful, beautiful cluster of stars. And maybe we'll get a chance to see, we'll see how the sky is doing for us, but maybe we'll get a chance to see M13, the Hercules star cluster, tonight. I'm actually going to end, let me just move forward here. We're going to end right down here with Vega and Lyra the Harp. We have kind of a constellation that's coming up. I wanted to show this because this is the beginning of our summer constellations. Lyra the Harp has a beautiful object right between these bottom two stars named M57, the Ring Nebula. A nebula is when a nebula is one of two things. It's either the death place of a star or it's the birthplace of a star. And they're actually related to each other. When a smaller star, like our own sun, sloughs off its outer layers, doesn't go supernova, but just sloughs off its outer layers, it produces this, which is called a planetary nebula, which is an unfortunate name because it has absolutely nothing to do with planets. Just early astronomers, they looked at these small, bright things and they thought, hey, I discovered a planet. They were wrong. They discovered a planetary nebula. That name has stuck around. That star right there in the middle of M57, the Ring Nebula, that's actually the white dwarf that sloughed off those outer layers into space. And then one more thing I'd like to bring up. April 21st, April 22nd, we have the Lyrid meteor shower. The best, so basically a meteor shower is named after the constellation where the radiant is located, where those stars or where those shooting stars are apparently originating from. A meteor shower is caused when the Earth passes through the debris left over by a comet. A comet is like this big dirty snowball, and as it gets closer to the sun, it melts and it releases all the dust and particulates and pebbles and rocks that are inside of that. And as the Earth smashes through this material, same time every year, we get a meteor shower, the same time and from the same general area. The radiant for the Lyrid meteor shower is near the constellation of Lyra the Harp. Hence the names the Geminids, the Leonids, the Orionids, etc., etc. So the best time to look would be to go on out the night of the 21st, the morning of the 22nd, after midnight. Probably around 2 to 4 a.m. would be the best time. Before we finish up here and we start our walk around the observatory, are there any questions about astronomy or any questions about the program that we had tonight? Yes?
So yeah, globular clusters. What causes those to form?
So a globular cluster, I was just thinking about a new analogy on globular clusters just today. So this is my first time trying out this analogy. The globular clusters formed very early on in the formation of our own galaxy and in the formation of other galaxies. So one way to think about it is that they're sort of like the